day has not been terrible.
I mean, you know, that line with power outage right now.
Yeah, I know. I heard about the power outage, and I know some people have got various issues with that. You know, apologize. Hope it gets rectified fairly soon. I do want to make a quick mention of something that I'm going to do a little differently today. If you took a look at the schedule, it looked like I was doing 6-4 today. 6-5 was going to be the next class. What I'm going to do is actually sort of a weird mix. I'm going to do 6-4 and 6-5. I'm going to introduce both of those both of those topics today. And what I'd like to do on Tuesday is just work on problems like I did with the last time. Just drop a whole lot of problems on you, let you work your time through them, and so on. That will basically wrap up chapter 6. I will spend about 3 or 4 classes on chapter 7. 10 and 12 are how we finish off the semester, but they're not terribly long. So everything should stay on track. We should be in good shape, even with that one day that I was off. So today what I want to do is talk about something called implicit differentiation. And specifically, this is going to reflect taking derivatives of non-functions. Now, when I mean a non-function, I'm talking about any curve, geometric shape, or such that fails that vertical line test, right? A circle is a good choice. Imagine that's a circle, right? I mean, I think we all agree that a circle is not a function. It does not satisfy any of those vertical line tests. It botches pretty much everything. Now, because of the fact that I'm not looking at a function, every value of x has the capacity to generate 2 different or more different tangent lines. All right. In this case, one tangent line in the first quadrant would have a negative slope. Tangent line that's in the fourth quadrant would have a positive slope. And so the slope of my tangent lines is not going to be determined entirely by a value of x, but it also has to concern a value of y as well. How do I figure out the different values of these derivatives? Again, since I'm not dealing with a function, I end up with multiple different spots where the curve exists for the same value of x. So how we actually go through the process is not that much different from chain rules. Right? So there's our chain rule. And in both of these situations, f and g were both functions of x. And we would put them together as a composite, and when I took the derivative, it would follow a somewhat predictable path. Now, suppose I just defined the letter y to equal g of x, right? I'm simply saying that y is itself its own function of x. If that's the case, then dy over dx is just the derivative of g, right? I would take the derivative of this little function. And again, this is something that we covered pretty much at the very, very beginning of chapters 3 and 4. Okay. Now, with this different definition, if I take the derivative of f of y, I'm going to get f prime of y times dy dx. Right? it does follow the chain rule exactly in form and structure. The only thing that's different is a tiny little bit of notation. So if I take the derivative of a function of y, where y is my variable, this is the typical form that I'm going to have. So if I take the derivative of x squared, hopefully we all get 2x. Right? If I take the derivative of y squared, I'm going to get 2y times dy dx. If I take the derivative of e to the x, I get e to the x. If I take the derivative of e to the y, I get e to the y times dy dx. And so on. Right? I take the derivative of natural log, gives me 1 over x. I take the derivative of natural log of y, I get 1 over y times dy dx. Okay. Everyone with me so far? Right. Mechanically, it's very similar to all the basic derivative rules that we've played with up to this point. So now, how does that help me here? Well, a circle is in the form of something like x squared plus y squared is equal to 1. That's a circle. Now, when I was taking the derivative of polynomials, I was just going term by term, piece at a time, and just taking the derivative of each individual piece. I'm going to do the exact same thing here. I'm going to take the derivative of x squared plus the derivative of y squared, and that's going to equal the derivative of 1. Right? Just like we did with polynomials, just do it one term at a time. Now the derivative of x squared is 2x. The derivative of y squared is 2y times dy dx. And the derivative of 1 is 0. All right. Now, the thing is, I'm not quite done yet. There's still a little bit to do. And the thing that I have to do is I need dy dx. dy over dx is a change in y divided by a change in x, which is very similar to delta y over delta x, and that's equal to slope. Right? I need my result to be dy dx is equal to something. All right? In order for me to get that, I need some algebra. If I subtract 2x to the other side, I'm going to get 2y times dy dx is equal to negative 2x. And dy over dx is going to equal negative 2x over 2y. If you want to, you can cancel out the 2's, and I just get x over y. Okay. So far, so good? Now again, I want to go back to my poorly drawn circle. All right. Before I started the calculus, I said that the slope of my derivative needed to be determined by not just the value of x, but whether I'm in the first quadrant or fourth quadrant. Specifically, there's a value of y that I need as well. So the value of my tangent slope is a ratio between negative x and positive y. It's not just determined by the value of one variable. It's one variable and the other variable. Okay. Does this make sense so far? I'm really happy. Now, I have encountered people in the past who, when they do this topic, they're not particularly happy with the topic, and they will try to fiddle with the equation before they take the derivative. And unfortunately, that's not a great thing. All right? A circle is x squared plus y squared is equal to 1. That's a circle. All right? If you decide to fiddle with it, and by fiddling with it, I say, okay, suppose you subtracted x squared to the other side, and you had y is equal to the square root of 1 minus x squared. And you're going to say, well, those are the same thing. No, they're not. All right? A circle is in the form of x squared plus y squared is equal to 1. This radical is that. It's just the top half. Right? If you try to turn it into a function, you have to throw away part of your curve. Because initially it fails the vertical line test. So if you do try to turn it into a function, you can't do it and keep your curve intact. So don't try to turn it into the square root of 1 minus x squared. Tackle it exactly as it says. Right? But just do it one term at a time. And then algebraically find dy dx. Okay. Another thing which I typically recommend to people, and this is just a matter of style more than anything else. When I went through the process, I was using dy over dx. Now, some people who have done this in the past might do this. Okay? Now, I'm not saying this is wrong. It's not. But as you're going through the process, it's really easy to lose that apostrophe. And I mean really, really easy. And then all of a sudden your y's and your y primes get mixed up. If you use a y prime, I'm not going to knock off points. But if you use dy over dx, that's a lot less likely to happen. Just saying. Okay? You're a lot less likely to flub it up. So, my little recommendation. So, let's give you a few examples and let you play. I'll give you guys a couple of minutes to try them. How are you doing?
Pretty good.
How's life?
That's been a while. Plus, it's not there 45 minutes ago, so I guess I'm not being that people.
We've got to get you one of those powered skateboard things.
Flying down the streets from the end.
I have children's to know it's our age.
That's cool.
With that, but
Shows up on a Segway. Would you like a hot shot? Sure. Especially since there's all manner of little tools around. See if people are still ready. All right. So, for the first one, I got x cubed minus y cubed is equal to 1. Again, take the derivative of each term at a time. X cubed, the derivative is going to be 3x squared. The derivative of y cubed is going to be 3y squared times dy dx. All right. And the derivative of 1 is equal to 0. So I subtract 3x squared to the other side. And dy over dx is going to be negative 3x squared divided by negative 3y squared. Or if you want to, you can get rid of the negative 3's. Either way. All right. For the second one, the derivative of e to the x is just e to the x. The derivative of e to the y is e to the y times dy dx. And the derivative of y is equal to 1 times dy dx. Okay. So now when I'm solving for dy dx, I'm going to want to get all the terms that have dy dx on one side. So that gives me e to the x is going to equal e to the y dy dx plus 1 dy dx. All right. Doing so allows me to factor out dy dx. So that gives me e to the x is going to equal dy dx times e to the y plus 1. All right. And since the goal is to get dy dx by itself, I now divide. And so dy dx is going to equal e to the x over e to the y plus 1. Everyone still with me? Awesome. The derivative of 3x squared is 6x. The derivative of 2x is 2. The derivative of y squared is 2y times dy dx. And the derivative of 1 is 0. All right. Get everything that doesn't have a dy dx attached to it to the other side. So that gives me 2 minus 6x. And I can divide by 2y. So it looks something like that. How's it sitting with everybody so far? Generally good? Now, depending on your algebra and the sequence of your algebra, you may have a different looking answer. For example, if I collected my terms on the other side of my equation and then solved it, it would look like 6x minus 2 divided by negative 2y. Which one is correct? They both are. They're both the same thing. All right. So if your answer does not match mine exactly, but all the terms are in the right place, and the only thing off is just a minus where it should be plus and vice versa,